Welcome everyone to another educational track series here. Today I wanted to take a quick look on ARM's recently announced version 9, or better, one specific feature of that, because the press release here, as usual, not the very most impressed, because AI security something, and very short of technical stuff of 100% world-shared data, Internet of Things, and 5G, obviously. But along the lines here, they mention SVE, Scalable. So ARM partnered with Fujitsu. Also, yeah, always ARM innovation, right? All their own. Partnered with Fujitsu. So also Fujitsu, of course, long high-performance computing with previously Spark processors, which is at the heart of Fugaku, world's fastest supercomputer. And building on that work, ARM has developed SVE-V and ARM version 9 to enable enhanced machine learning, digital, also, and again, very short on technical details. So the technical details are as following. Here I'm using paper, the previously Scalable Vector Extension. I guess SVE-V is mostly the same, but what I wanted to point out recently, we had a video a year ago or so regarding RISCV-V vector extension that I liked very much and was mostly impressed with. And what this does is, and ARM Scalable Vector Extension is sort of similar, if of course different instructions and architecture, but otherwise similar. And what this does is not repeating the mistakes that Intel made. I made here a short little text file. So on x86, when we went there, Intel went there from to a single instruction multiple data as AMD with MMX, they just reused the floating point registers, 64-bit of not extended 80-bit formats, and allowed them to split them in ints to process, for example, 232-bit or for 16-bit ints at a time, for example, for RGB graphic processing. And AMD did something similar, but they said, hold my beer, ints suck a little bit for a lot of game logic stuff and so on, and they also allowed floats. This was 3D Now for those who are so long in that field. Intel, of course, then hold my beer and added floats as well to what was then called SSE. And then was SSE 2, 3, 4 was probably cancelled. AVX extended that to 128-bit. Before this was 64-bit of those, and AVX2 of latest and greatest, more modern fame, 256 bits, and AVX 512 for. So the reason we or Intel and AMD and wider bits are preferable is that with one instruction you run at 5 gigahertz, and of course the more instruction you have only so many instructions you can run with at 5 gigahertz, and so the more bits and bytes and floats you can process with one, which is why they are wider and wider. The also, yeah, there was actually PowerPC, Ultivec 128-bit, and UltraSpark with visual instruction set, 64-bit integers for the most part. So, and the problem with wider is, or the problem on the x86 side in general is that usually you program one thing, AutoCAD or your favorite game, and like Crysis or so, and then you have a new CPU, and it's not getting magically faster, even though your latest Intel CPU might have AVX 512. Your good old-fashioned software does not even use them. And on the Linux side, our source distribution and other stuff, you would even need to recompile that. So you can recompile for AVX 512, but you have to. So a lot of software either has specially compiled DLLs or shared objects on Unix, and or other per function of generating some object codes twice without DLL statically compiled in. But you need to compile that, or yeah, if you are lucky and this compiler supports that, or you otherwise need to write assembly by hand. And this is a huge scalability problem on the x86 side, and this is why I was happy to see the RISC-V folks having this variable, how do they call this, sized vectors, so that You can have a RISC-V CPU with just 64-bit or anything up to, I don't know, 2048 or something of that sort. And the way this works is it here even, oh no, I should not have scrolled that here, so traditional vector, so variable vector length. And the way this works is having the software in assembly, of course, generated from C, C++, Rust, work with the hardware flexible of loading whatever fits in the hardware. So you configure the hardware to, hey, I want 16-bit or 32-bit ins of loads or something, and the hardware then has some variable lengths. Some CPUs might have 128 bits, latest and greatest, and some years might have 1024 bits, and the hardware just loads more of them and processes more data. Of course, the devil is in the detail, and this obviously needs to very specifically constructed for work. And I'm relieved to see ARM is following this flexible variable length vector extension, and similar to RISC-V, and they write here to, for example, exactly that, at least where was this, allowing CPU design. So second was a desire to introduce extension, multiple implementations, vector lengths more suitable for power performance. So this might be some embedded system with power targets, might have something else, and latest and greatest supercomputer silicon, and yet the same code. And that is the beauty of this. By design, the same code compiled from C, C++, Rust, or handwritten machine assembler code can run on an embedded system with 128-bit or on a supercomputer with whopping 2048-bit. ARM believes they achieved this goal, allowing any flexible vector register lengths between 128 and 2048. Support vector length agnostic programming model. Exactly the stuff that I previously came pretty impressed on the RISC-V side. They have here some nice graphs to better illustrate that. You have here registers, SVE registers, usually like registers where the code can either, like CPU ID, like determine what is the vector length, or otherwise configure them to split this here in, for example, what do they have here, 16 or so bits. And here you see this 256-bit vectors. I just need to be a little careful that this is not hidden there. 256-bit vectors, 64-bit elements. This is similar to what we previously had here, MMX, SSE, AVX, splitting those registers, for example, RGB, X, Y, Z, W, or similar such stuff. And here they have 256-bit vectors, 32-bit elements. And as you see, this is exactly, of course, a nice visualization of what I meant. Loading data from your program, whether they, of course, write AI and machine learning, but of course 3D, audio, MP3 or Vorbis Opus, all the latest and greatest, and X265 or H265 and AV1 and so on, loading their pixel data from the videos and processing them. And this is, of course, the speed up that is achieved with single instruction multiple data. And I'm really happy to see that ARM moved to this direction, to vector length agnostic instruction set architecture. And yeah, yet another point what will make all those processors, whether RISC-V or ARM, so much better than what the convoluted history of everything from MMX over SSE to AVX2, and of course in the latest and greatest Intel advanced vector math has to offer. I'm probably going to try this out. The problem is right now I'm not sure if, or I think Intel Apple's M1 does not support this yet, but correct me if I'm wrong. I think so far this is a Fujitsu supercomputer thing, and upcoming CPUs, but I will probably experiment this with some emulation at least, or we will see. And here in the previous video I already had this presentation here from some blog explaining this in detail, how this works. this is probably a good read for you. Probably I should paste it here. I also leave it in the comments below. And I believe there are some proof of concept implementations for RISC-V. There maybe even, actually we could check that here, of Scalable Vector Extension. Apparently not in this GCC, but given Fujitsu is running this on supercomputer, I believe there probably should be some support somewhere. So this is a very good run through here on the RISC-V side. And otherwise, of course, this presentation, let's also directly paste. It's also here, copy and paste only works there every second time, but it could be reverse, it could also work never. So yeah, this is how this looks. Then here, for example, the resulting code, so the load, of course, this is in general loading here the loop variables, and then while lt load loop here, loading that but of course on the first glance, if you're not familiar with assembly and stuff, it certainly does not say much. Probably for most people this visualization is probably the best to work with and understand this. Here's also a nice cycle by cycle example here, loading the data, so the instructions and how this loads here the values. And as you see, of course, loading twice as many data, single instruction, multiple data here, compared from 128-bit to 256-bit. Certainly very nice visualization, and this is what is a little bit frustrating in this press announcements of like, yeah, you had me at AI and something self-driving cars and Internet of Things. Anyway, for me again, this is a difference between, and this is also what increasingly will people drive away from x86. And this is the whole thing, so why I'm so excited about this, and you don't see me that often here that excited, because this is a good engineering solution, right? The x86 stuff is just a convoluted mess. It's just like someone at Intel had some idea. Actually, the MMX stuff is from some i860 or i900, whatever, something of that sort. And it was not forward thinking, right? It was just a slapping there something on the processor to have some multimedia extension. And I would also encourage people, and in general the industry, to think this stuff a little bit more through. Of course, my tiny little channel cannot make such a big difference, but on the x86 side, we had now 20 years of this convoluted stuff that is not forward compatible, and just working with higher performance. And imagine how much more successful, or also faster, right? It's even for the user. You have some last year's AutoCAD version, and on your new CPU it runs twice as fast, for example, or your latest and greatest games. And with the mess that is SIMD and x86, you need a new version, you need to recompile or patch their assembly and so on. And I also should point out, however, that on the ARM side it was very convoluted, right? ARM is otherwise known for also having similar mess. Actually, I should have, they basically had VFP 1 and 2 and Neon, and actually the whole floating point was a mess. Neon, is there some nice overview somewhere? Yeah, complex floating point compiler options, because yeah, VFP, as I said. So this was a huge mess so far, so I'm relieved that ARM is not continuing that route. They could have, similar to Apple, slapped on there some Neon 512 or something, and I'm happy that they haven't. Of course, ARM is also in a position that they want to support embedded to high-performance supercomputers these days, so a flexible solution like that certainly makes sense to cover the whole spectrum. In the previous video I showed a performance analysis here of RISC-V people, and this looked pretty good, right? Here again, even MIPS, AVX2 and RISC-V, and how compact this is, and yet vector length agnostic. Oh, was this even, wait a second, is this even the, oh no, this should be RISC, no, this is vector. And yeah, very few instructions, pretty high performance, and that is certainly nice to see, and exactly what you want to see from future instruction set architectures. I hope with that, maybe I even encourage some people to work in this field or go get more into low-level assembler optimized machine code, and or for example RISC-V, right? RISC-V is open, so RISC-V, this is not formal. Where do we, all right, I probably didn't, here is that, let's see if that, yeah, that's not what I wanted, but here we have it. And this is not final. I'm not sure if there is already silicon out there on the RISC-V side, and you can still work on this, right, and contribute to this. This is of course recurring difference of open hardware, and here's this elements per vector register stuff for different vector lengths and so on. So again, hope you learned something and enjoyed this low-level, very deep insight look to modern CPU architectures. And in what they talked about yesterday, did you? Don't even quite, or part of it, VLISVI, did you post that? Don't even quite, but anyway, thanks for that. Murali asks, maybe stupid question, but ARM better in terms of performance and efficiency? Why does x86 exist? Is there any advantage? Well, x86 purely exists due to the historic being at the right place, or mother working at IBM and stuff, although that was probably Bill Gates and not Intel. But just being at the right place, being there early, and just by luck and business practices from the IBM 8086 or XT80 and so on, each year, basically they exist due to this binary compatibility that nowadays is a little bit convoluted, and yet at the time usually delivering okayish performance for the price, or at time good. One could also call it good. Of course, there often was stuff faster, DEC Alpha, MIPS, R10K, PowerPC, and so on. At times the stuff was faster, but often also a year later, or regaining the performance chrono a year later. But the other stuff was also usually more expensive, right? Especially SGI MIPS, Motorola IBM PowerPC. Anyway, the PowerPC stuff of IBM AIM, was it AIM Alliance of Apple, IBM, Motorola. PowerPC stuff, due to the nature of IBM and PowerPC, usually more expensive, even though at times it was faster. And this is also what I wanted over the next years. Of course, I have a collection of vintage stuff. So as you see, we're not only doing the vintage stuff, but also the latest and greatest. But I also wanted to do some more latest GCC performance comparison, because back in the day you couldn't compare that easily, PowerPC with different compilers on macOS or IBM AIX than on Windows or other sites. Thank you for the super chat there, highly appreciated. So yeah, why is x86 there? It exists due to market presence and the historic compatibility, and certainly Windows, the usual Windows and Intel, the Wintel cartel there, and not through particular technical excellence. So yeah, the advantage, basically the only advantage is binary compatibility, which for programmers advancing that, and also the latest and greatest state of performance, difficult to keep up with as seen in Apple's M1 processors. Intel implements a lot like departments as well, which is other implementation. Emulation says Intel AMD have so much optimization already done that they can make 4 GHz processors all cores where RISC is really needed for low power mainly. Well, actually, as seen in, well, RISC was also performance, right? 20 years ago, RISC, of course, PowerPC, DEC Alpha, MIPS, R10K. State-of-the-art performance, usually faster than Intel. Of course, the modern x86 CPUs translate internally dynamically x86 to internal RISC like micro-ops. And nowadays, of course, ARM is interestingly pushing to or being successful in high-performance computing, while on the desktop side, well, on smartphones, obviously pretty good performance, especially the high-performance Apple One, and bringing that to the desktop. So far, of course, the M1 giving Intel CPUs quite a run for the money. So I also recurrently question here how much Intel and AMD can advance the performance, because it is clear to me, given how convoluted the instruction set is, variable length encoding, very difficult, if not next to impossible, to make this even wider issue, because it's simply so much easier, and with easier also less logic gates. Less logic gates mean better timing, because the biggest issue there is also the variable length, so you can't even parallelize the variable length decoding there of x86 instructions, which is why Apple's M1 processor now is, what was it 6 wide issue versus 4 wide of latest. Anyway, it's 1 or 2 instruction wider issue than x86 there. So we can't simply say anymore that this is for embedded and stuff. So that's probably it for this video. We try to keep it shorter here, otherwise less people watch it later, and we certainly want people to learn something. I hope you enjoyed this, and don't forget to share, like, and subscribe for the next videos and technical insights here to come. Maybe we continue 15 minutes. Theoretically, we have some Thunderbird to update there on the more live channel. If you're new to this stuff, this is the main channel. We have some more live channel there in the channel list. So could also do some 10 or 15 minutes open source package update stuff. Otherwise, hope to see you soon for the next fun stuff to come.